Well, welcome back. This is Unit 2.5, Chemical Analysis, and that's page 343 through 351 in your textbook. So please make sure you read that. That's really important. All right, in chemical analysis, what we're trying to do is determine formulas. And one of the first steps that we are going to take in doing this is learning about percent composition. And if you'll write this definition down, percent composition is the percent of a compound's mass contributed by each type of element in that compound. Okay, so let's review what a percent is. We've learned early on in grade school that a percent is a part of a whole. Like if you were at Thanksgiving and your uncle ate a half of a pie, he ate the half of the whole pie. So what percent is that? 50%. Okay, because let's say we divided the pie into 4 sections. He ate 2/4 of it, or 1/2. 1 divided by 2 is 0.5, and so change that to a percent, and that's 50% of the pie. Okay, now we can do that same thing with compounds. For example, H2O. We all know what H2O is. H2O is water. So if we take the entire molar mass of water, so for hydrogen, we learned how to do this in 2.4. There's 2 moles of hydrogen in water, so 2 times, and hydrogen's mass is 1.01. That's going to give us 2.02 grams per mole. And then oxygen, there's 1 mole of oxygen. There's no number written here, so it's just 1 of oxygen. So 1 mole of oxygen times the molar mass of oxygen is 16.00. That's equal to 16 grams per mole. Then if we add that up, then we get 18.02 grams per mole. That's the total molar mass of water. So if we take, and we want to know what percent of this is hydrogen, then we take the part that hydrogen contributes, which is 2.02, okay, divided by the whole thing, which is 18.02, and then multiply that by 100, and we're going to get the percent contribution of hydrogen to this molecule. All right, and so I'm going to grab my calculator and I'm going to do 2.02 divided by 18.02 times 100. And that's going to give me 11.2097. Okay, so 11.20976. Okay. And I'm not going to round that yet. And I'll tell you why in just a moment. All right, now we're going to take and we're going to get the part that oxygen contributes to this. So this is 16.00 divided by 18.02 times 100, and that's equal to a certain percentage. Okay, so again, grab your calculator. We're going to do 16.00 divided by 18.02 times 100. That's going to give us 88 point, let me write that here, 88.7902. Okay, all right, so now for this, I'm going to, how many do I round it to? Okay, so it doesn't say. We don't have anything in the given that tells us how to round this. So nothing is given like this, and we're working with molar masses, I always have you round molar mass to 2 decimals. On your periodic table that you're using, it's always round to 2 decimal places. So we're going to round these percentages to 2 decimal places. So here's the first, here's the second. So this would round this to 11.21 and this to 88.79. Okay, now when I add these two together, it should equal 100%. So 11.21 plus 88.79. And this is just a way to check your work. Okay, and indeed it does add up to 100%. Okay, so that's percent composition. Determining the percent of a compound's mass contributed to each by each type of element in the compound. Okay, so here's another way. Here's another example of how to do percent composition. Now, in my example that I used, I took a part of a whole and I figured out the molar mass, and I used that mass of hydrogen based on the number of moles. So in this example, what they're doing is they're converting moles to grams. So it says here, what is the percent composition of sugar with the formula C12H22O11? So what they do is they look at this formula and they say there's 12 moles of carbon. So that's where they get the 12 moles of carbon here. So in this formula, there's 12 moles of carbon. Okay, so I'm going to take this 12 moles of carbon in 1 mole of the whole thing. Okay, 12 moles of carbon in 1 mole of the whole entire molecule. Okay, and so they see, what do I want to get rid of? Well, they're getting rid of the moles of carbon. Okay, and so they put the moles of carbon on the bottom, and we want to convert this to grams. So they're putting grams on top, and in 1 mole of carbon, there's 12.01. They're rounding to 1 decimal place. So it's 12.01 grams of carbon. And they get this number right here from the periodic table. Because remember, the periodic table is in grams per mole. Grams per mole. Okay, so they get that from the periodic table. Well, moles cancels moles, and that leaves grams of carbon per, and then this is 1 mole of this. Okay, so either way you do it, whether you're doing it conversion or you're doing it my method that I did over here, you're going to get the same percentage, okay, or the same mass. So they take this 144, that's part of the whole. So what they do is they add up all of these. After they get the mass of each one, they add it all up, and so that's the 342.0. So they take the part, which is this, over the whole molar mass, which is this, okay? So 144 divided by 342.0 times 100, and they get 42.1% carbon, 6.4% hydrogen, and 51.5% oxygen. Okay, so 22 divided by 342, and then 176 divided by 342. So here's the hydrogen here and oxygen here. Okay, so this is carbon, hydrogen, and oxygen. So it's the same thing we did, only they're going about it a different way. They're taking the moles per the whole thing and doing a conversion. Okay, whatever way you're more comfortable with, that's the way that you need to do it. All right, and so to make sure this is correct, we're going to add all of these percentages up, and it should equal 100%. Okay, so 42.1 plus 6.4 plus 51.5, and it does equal 100%. Okay? All right, so let's do an example of our own. So ibuprofen is a common pain reliever and anti-inflammatory, and its formula is C13H18O2. What is the percent composition? Okay, so go ahead and pause the video and see if you can work this out. Okay, so here we have carbon, and we have 13 moles of carbon in this 1 whole mole of this. Okay, so 13 times, what's the molar mass of carbon? 12.01. Okay, now hydrogen, we have 18 moles of hydrogen. Okay, times the molar mass of hydrogen, 1.01. And for oxygen, we have 2 moles of oxygen times 16.00 is the molar mass of oxygen. Now this 12.01, 1.01, and 16.00 I got from the periodic table. This is the molar mass of carbon. The 1.01 is the molar mass of hydrogen, and 16.00 is the molar mass of oxygen. Okay, so I'm going to multiply these out. Okay, so 13 times 12.01, and I get 156.13. And this is grams per mole. Okay, grams per mole. All right, 18 times 1.01 is 18.18 grams per mole. I don't need a calculator for that. And 2 times 16, I don't need a calculator for that either. That's 32.00 grams per mole. All right, now add this up. So I have 156.13 plus 18.18 plus 32.00, and I'm going to get 206.31 grams per mole. So this is the molar mass of ibuprofen right there, the C13H18O2. That's the molar mass. All right, so to get the percent composition, remember, a percent is equal to part of a whole. Okay, so I'm going to get the percent of carbon. So the percent of carbon is equal to 156.13 over, that's the part that carbon contributes right there, over the whole thing, which is 206.31. Okay, I'm going to multiply that by 100 to get it into a percent. Okay. Now, I'm going to go ahead and set the other two up. So the percent of hydrogen is going to be equal to 18.18 divided by 206.31 times 100, and that's going to give us our percent of hydrogen. And the percent of oxygen is going to be equal to 32.00 divided by the whole thing, again, 206.31 times 100. That's going to give us our percent of oxygen. Okay, so let's go ahead and pick up your calculators and let's do that. So 156.13 divided by 206.31 times 100 is going to give us 75.68. Okay, 75.68. Okay. All right, on the next one, 18.18 divided by 206.31 times 100. That's going to give us 8.81. Okay. And for the last one, 32.00 divided by 206.31 times 100. That's going to give us 15.51. Okay. All right. So that's the percent composition of each one of those elements that make up the compound ibuprofen. Now, if I want to check my work to make sure that I did this correctly, I'm going to take 75.68, add it to 8.81 and 15.51, and I get 100%. Okay, so that lets me know that I did my math correct. Everything is good there, because these are the only 3 elements in this compound. So that's 100%. Okay, so from this, we can get empirical formulas, molecular formulas, and structural formulas. Well, really, a structural formula is just a representation of the molecular formula. We're going to talk about that real quick. All right, so here's 3 definitions that I need you to write down. So go ahead and pause the video and do that. All right, molecular formula. Molecular formula is the actual or true number of each type of atom that's in each molecular compound. And this is what we've been looking at so far in chemistry. CO2, okay, that's carbon dioxide. That's the actual formula of carbon dioxide. H2O, C13H18O2, and we've also talked about H2O2. All right, so those are actual true formulas. That's called the molecular formula. The empirical formula. Now, this is the simplest integral ratio of the different types of atoms that are in the compound. For example, if we have C2H4O2, okay, and this is the molecular formula. We're trying to get a molecular formula. We're going to look and see all of these subscripts have a common factor of 2. So we're going to factor it down using that common factor. So if we factor this 2 down with a 2, that leaves 1. Factoring this by 2 gives us a 2, and this one gives us a 1. So the empirical formula for this true formula is C1H2O1, but we don't write the ones, so it's just CH2O. Okay? So each of the subscripts were factored by a 2. Now, some empirical formulas cannot be simplified, like carbon dioxide here. You cannot factor this down anymore, okay? And H2O, you can't factor that down anymore. Or the same one right here. We can't not factor this down anymore. That's the simplest form that it's in. However, H2O2, which is hydrogen peroxide, can be factored down. So what would be the empirical formula of H2O2? Well, each one of these 2's has a factor of 2 in common. So if we factor that down, we're just going to get HO. So this is the empirical formula of hydrogen peroxide. Okay? And empirical formulas are really important. The purpose of an empirical formula, its only purpose is to aid us into getting a true formula or molecular formula from a compound. Okay, it's an analysis technique that identifies compounds or molecules, and it's very, very, very handy and popular in chemistry. It's what we call an chemical analysis, which is what this whole section is about. All right, and then the structural formula shows how the atoms in a molecule are arranged. And you may have seen some examples of structural formulas, like this one right here. This shows us that, we have 2 carbons that are bonded with 3 hydrogens, 2 oxygens, and 4 hydrogens, another hydrogen here. Okay, this is called a Lewis structure. We're actually going to draw these this year. Okay, and this one is called a ball and stick because each of these spheres, each of these round circles represents an element, okay? And then they're connected by these little lines, which are sticks, okay? We'll look at a couple of these, but not too many, okay? So this is just another representation of a molecule. And you may have seen things like this when you pick up your prescriptions that have all of this information, like this information pamphlet inside the prescription or stapled to the outside. And sometimes they give the structural formulas of the actual medicine that you're taking. It looks something like this or something like this. Okay, so either way. All right, so if you know the percent composition of a compound or molecule, then you can work backwards to determine its empirical formula. And then from the empirical formula, you can determine the true molecular formula. Okay, and like I said, this is a very handy technique for chemists. So let's look at this example. We have 48.65% carbon, 8.11% hydrogen, and 43.24% oxygen. So you may be asking, well, where do you get these numbers? Well, like again, if we're having a chemical analyzed for some reason, then we run it through a spectrophotometer. And what it does is we run the chemical through this machine. And what it does is it breaks down the chemical and tells us that it contains carbon, it contains hydrogen, it contains oxygen. And of these three elements it contains, 48.65% of it is carbon, and 8.11% is hydrogen, and 43.24% is oxygen. So we get this printout that says these percentages, and then we can use a technique to actually come up with an empirical formula. And then from that empirical formula, we can get a molecular formula, so we can actually identify compounds that we didn't know the name of before. Okay, so when we're given these percentages, there's an assumption that we have to make. We have to assume that we have a 100-gram sample of whatever that compound is. Okay, and then the calculations become really, really simple. And there's a saying that you need to write down and remember, and it's going to help you do these. So it's 4 lines. The first line is percent to mass. Second line is mass to mole. The third line is divide by the smallest. And the last line is make them whole. So if you'll memorize this, percent to mass, mass to mole, divide by smallest, make them whole, then doing an empirical formula is a piece of cake. Okay? All right, so let's take our same problem and let's do that. And so some people work in rows. I like to work in columns. That's just how I learned to do it in high school, and that's just the way I've kept it up. All right, so I'm going to put carbon, hydrogen, and oxygen. Those are the 3 elements that I have in this compound. Okay, and 48.65%, 8.11%, and 43.24%. Okay. All right. So that's my givens. I've written it down. Now I'm ready to start my calculation. All right. So step 1, percent to mass. Okay. Very, very simple. If we assume that we have a 100-gram sample and we have these percentages that add up to 100%, then when we do percent to mass, all we have to do is take this exact same number and put grams there. Okay, same thing with here, 8.11 grams and 43.24 grams. All right, so that's our first step, percent to mass. Okay, second step, mass to moles. So what that means is I need to take these masses and I need to convert it to moles. So luckily, we learned that in 2.4, 48.65 grams over 1. Okay, so what do I want to get rid of? Grams. And what am I converting this to? What conversion factor can I use here to get this into moles? Well, if you remember back to the mole map, to go from grams to moles, we need to use molar mass. Okay, so moles. So this is the molar mass of carbon. So 1 mole of carbon is 12.01. We get this from the periodic table. What can I cancel? Grams. Do I have the unit that I want from our answer? Well, we're trying to convert these to moles because the second step is mass to mole. So the answer is yes. So all I have to do is take this and divide by 12.01. Okay, so pick up your calculator, 48.65 divided by 12.01. And that's, don't round this. It's very important that you do not round until the final answer. Okay, so I'm not going to write every single one of these digits down, but I like to carry it out to like 5 decimal places. Okay, so I have 4.05079. Okay, 5 decimal places gives me enough decimal places so that I don't make a rounding error. Okay. All right, so percent to mass, mass to moles. So this is moles. Okay, so we need to do the same thing here. Well, let's look at what we did here. We took this mass and we divided by the molar mass. Okay, so you can set this up every time, but if now I know I just have to divide by the molar mass, then I'm going to take and just do that without writing it down. So 8.11 divided by the molar mass of hydrogen is 1.01. Okay, so that's going to give me 8.02970. Okay, and that's moles as well. All right, and so 43.24 divided by the molar mass of oxygen, which is 16.00, that's going to give me 2.7025. Okay, there's not a fifth number out here. So that's the whole thing right there. And this is moles. All right, so we've gone percent to mass, mass to mole. Now the third step is divide by the smallest. So what we're going to do is look at these 3 values for moles, and we're going to divide all of them by the smallest one. Well, the smallest one here is 2.7025. Okay, so I'm going to divide all of these by the smallest number we got. 2.7025 moles. Okay. All right. So one of them, whenever you do, every single time you do this, one of these is going to come out to be 1 because you're dividing it by itself. So this one is 1. So we need to divide this one. Okay. So we have 8.02970 divided by 2.7025, and we get 2.97, and that's all I'm going to write down, just these 3 numbers, and I'm going to tell you why in just a second. All right, so now let's do this one. 4.05079 divided by 2.7025. Okay, and I'm going to get 1.49. Okay. All right. So percent to mass, mass to mole, divide by smallest. Last step is to make them whole. All right. So I have a 1, a 2.97, and a 1.49. Now, I need to make these whole numbers. Well, 2.97 is practically, we're only 3/100ths of being a 3. Okay, so when you're really, really close like this, and you're going to get numbers that are really, really close most of the time. So if that's really, really close like this, I'm just going to say that's 3. Okay, now look at this one, 1.49. Well, this is only 1/100th away from 1.5. Now, you might say make this whole. Well, 49 really does round down to 1, but 1.49 is closer to 1.5 than it is anything. So rounding up by 3/100ths of a point is okay, but rounding down or up by 0.1, that's really too much to round. But we can round this to 1.5 because it's only 1/100th away from 1.5. So that's what we're going to do. Okay, so now if we look at this, 1.5, 3, and 1, make them whole. This still is not a whole number, but it's easily multiplied by a whole number to get a whole number. Now, what do I mean by that? What can I multiply 1.5 by to get a whole number? What whole number can I multiply this by to get a whole number? And the answer would be 2. 2 times 1.5 is 3. So what I'm going to do is I'm going to take, and if I do it to 1, I have to do it to all of them. Okay. I'm going to multiply all of these by 2. So 2 times 1.5 is 3. 2 times 3 is 6. And 2 times 1 is 2. Now I have whole numbers. Okay. Now these whole numbers represent the subscripts that go for carbon, hydrogen, and oxygen. So this is getting an empirical formula. Remember the empirical formula? So my empirical formula for this compound with these percentages is C3H6O2. Okay, that's my empirical formula for this. All right, so that's how you get empirical formulas. Now, we can take this one step further, and if we know just one more piece of information, we can get a true molecular formula and then identify the compound. We cannot identify compounds with just empirical formulas. Okay, that's impossible to do. We have to have one more piece of information. So to get the empirical formula to the molecular formula, we need right here the molar mass. Okay, so this problem gives us the molar mass. So let's do another example. It says here that a small sample of an unknown compound at a crime scene was analyzed through a spectrophotometer. That's the machine I was talking to you about. You put it into the spectrophotometer and it spits out percentages. Okay, 4.51% carbon, 1.13% hydrogen, and 6.01% oxygen. Okay, it was also determined that the molar mass of this compound was 62.08 grams per mole. What is the molecular formula of this compound, and what is the identity of the unknown compound? Okay, so when it gives you a molar mass of a compound, we can get the molecular formula and identify the compound. But first, we have to get the empirical formula. All right, so let's take our givens right here. And this is for hydrogen, and this is for oxygen. We're going to use our technique called glues, and we're just going to pull them out and list them. Okay, so I know we have carbon, hydrogen, and oxygen. All right, so for the carbon, I have 4.51%. For the hydrogen, I've got 1.13%. And for the oxygen, I have 6.01%. Okay, here's also a piece of information. So I'm just going to put molar mass is equal to 62.08 grams per mole because that's going to be important in just a minute. All right, so we can do the molar mass of this. I'm sorry, empirical formula. All right, so step number 1, percent to mass. So all we have to do is just change these percentages to grams. So 4.51 grams, 1.13 grams, and 6.01 grams. Boom, percent to mass. Mass to mole. All right, so just like on this other one, we're going to divide this by the molar mass of this compound. I'm sorry, this element. So that's carbon 12.01. So we're going to divide this by 1.01. And we're going to divide this one by 16.00 because that's oxygen. Okay? All right, so let's go ahead and do this. 4.51. Oops, my calculator turned off. All right. 4.51 divided by 12.01. Okay, that's going to give us 0.37552. All right, 0.37552. All right, 1.13 divided by 1.01. Okay, that's going to give us 1.11881. Okay, 6.01 divided by 16.00. That's going to give us 0.37563. Okay. All right. Percent to mass, mass to moles. So these are all moles. Divide by the smallest. Well, we have two of them right here that are almost the same number. So 5263. So this one is the smallest. So we're going to divide all of these by 0.37552. Okay. 0.37552. 0.37552. Okay, that's basically 1. That's basically 1. Okay, so we need to divide 1.11881 divided by 0.37552, and we get 2.98. Okay, 2.98. 2.98 is only 2/100ths of a point away from 3. So I'm going to go ahead and round that to 3. All right. So our formula is CH3O. CH3O. Okay. Now, it's given us a molar mass of this. Now, to get the true formula, what we're going to do is we need to get the mass of the empirical formula. So we have C, which is 1, H, which is 3, and O, which is 1. Okay, we need to get the mass of this. So carbon is 12.01, hydrogen is 1.01, and oxygen is 16. All right, so this is going to be 12.01, 3.03, and 16. We're going to add these up. Okay, 12.01 plus 3.03 plus 16. That's going to give us 31.04 grams per mole. Okay. Now, what we're going to do is compare the empirical mass with the true molecular mass, molar mass that we were given. And we can very quickly see that this is a factor of 2. So if we take 62.08 and divide it by this, then we're going to get a number 2. Okay. So this mass is twice this mass. So if this true mass is twice this mass, then the empirical formula, the molecular formula, is twice the empirical formula. So the true formula for this is C2 H6O2. Okay, so we can go to Google and we can put that in just like this. So let's see, let's open up a Google page and pull this over. All right, so what was it? C2 H6O2, and hit enter. And it tells us that this is ethylene glycol. Okay, so chemspider.com, I guess that's it's not Wikipedia, right? Wikipedia has an entry here. Okay, so PubChem says it's ethylene glycol. Let's see if we can get a third one. All right, sigmaaldrich.com. Here, ethylene glycol solution. All right, so we've looked at 3 different sources. So we compared each one of those sources, said ethylene glycol. So this is ethylene glycol. So we just identified the chemical at the crime scene. And if you don't know what ethylene glycol is a common name for antifreeze. Okay, so it was antifreeze at the crime scene. And antifreeze is a poison. If you were to ingest antifreeze, it shuts down your kidneys. And when your kidneys shut down, then your whole body shuts down and you die. Okay, So that's getting a molecular formula from an empirical formula. All right, that's it. Make sure you slap that like button right across the face. Give me a thumbs up and a subscribe.